Hello. The title of my presentation is Branch Regulation, Low Overhead Protection from Code Reuse Attack. This is paper information. This paper was presented in ISCA 2012. I worried about this topic is unfamiliar with most people, most students. But nowadays I'm into computer security, so I choose this topic. This is abstract. The main idea is quite simple, but to understand what is the problem is too difficult for me. So I have had to study a lot of other paper. Anyway, the main idea is this paper proposed branch regulation solution. It means a lightweight hardware support protection mechanism against code reuse attack. I have never heard about code reuse attack, so I have had to study. Code reuse attack is like this. Attacker, at first, attacker can exploit using a buffer overflow, and they change the program flow, and then attacker can inject some malicious code or use some existing system library code. In this case, we call code reuse attack.
So in this case, for code reuse, they don't have this virus code or one code.
Yes, just buffer overflow code.
Okay, so just buffer overflow, sneak into their system,
Yes.
and then they just use the system. Are there any characteristics of this kind of code or library that are used by these attackers? Why do they attack those kind of code?
Let me explain.
Okay.
There are some code reuse attack. ROP, called return-oriented program attack, is one of the most common code reuse attack. Attacker should identify gadget. Gadget means some sequences of instruction in victim's program. This is existing code, not a attacker's code. It should be end with a return statement, because if there is no return statement, attacker cannot change the flow of the program. So gadget should be end with the return statement. This is one example of ROP attack. This picture from the other paper. The attacker used a buffer overflow attack, and they changed the program flow. And these are gadget. This is the existing code in system. Attacker just use them. Attacker cannot change this code, and they finally learn their shell code. It means they take some root function, root privilege. This is ROP attack.
Can you explain step by step? There is 1, 2, 3, 4, 5.
Actually, I don't know exactly, but have you ever heard buffer overflow attack? When we write some data to buffer, sometimes it overrides the adjacent memory block and overrun other memory buffer. It is kind of memory safety violation. So attacker can use the vulnerability, and they change the program flow.
You don't know the detail.
Yes.
Okay, so let me have a pointer. Okay, so let's say this is a buffer. So this is usually on the stack. Okay, stack you have buffer. This is a local variable. Okay, so this you read some string from the remote system, remote attacker. They usually type maybe command line. Okay, and then they write into this buffer. Okay, write into this buffer. And usually the buffer, the vulnerability means the system and the original application running on the server should check the size of this buffer. Because if you don't, they check the size, then this input buffering system, usually the command written is usually while end of carry return, you read all these commands. And they override this buffer. Okay? So override adjacent variable. Finally, they override the return address. Remember, in the stack frame, you put your return address before you call other function because you have to know which address you have to come back. If you override return address, what the usual buffer overflow attack is, you actually copy, in this buffer, you copy this one code, virus code. And then when you override this return address, you override the start address of this virus code. So when you return, you actually go to the beginning of this virus code and you are running your virus code. That's the usual buffer overflow. Okay, understood? That's what this is. This is. Okay, new code, which is virus code. They are running their virus code by modifying the return address. And reuse attack, my guess is instead of modifying this return address to the beginning of new virus code, they can modify this return address to go into some of the library code. Because usually library codes are open, right? Everybody can access, and they know the behavior. And they can use, they don't have to write their virus code. They can use existing library to do what they want to do. So they change their return address to go into their library, which they are targeting. Okay, and they can go back and forth using this mechanism. By reusing the library code, they can implement what the virus is doing. Right? Either more secret way because they don't have to be code. They are using they are running their system. Okay, that's my guess. Understood?
Okay, clear.
Okay. This is my guess. You have to find out more details. Understood?
Yes. Another code reuse attack case is JOP attack, jump-oriented programming attack. This is a new class of code reuse attack. It means anti-return-oriented program attack depends cannot prevent JOP attack. So this is the motivation of this paper. A JOP attack statements end with jump branching.
JOP is what? Jump
statement.
So their focus is the previous. Let's go back. I don't remember the name. Okay, the next one. No, next one. Next one. Okay. Are they targeting the ROP or others? JOP.
They targeting both of them.
ROP or JOP. And ROP is changing return address. JOP is changing the register. For
Yes,
interaction.
that's right. Using
Right.
register. Use register.
Right. They should modify the register.
Yes.
Otherwise, they cannot change.
Yes.
Okay. They're targeting both.
Yes.
How?
Let me explain. JOP attack use a dispatcher table. This table made by attacker. They doesn't use a stack. This is a comparison between ROP or JOP. ROP use a stack, but JOP attack use dispatcher table and dispatcher. These gadgets is the existing code, and dispatcher and dispatch table are made by attacker.
So, I guess jump-oriented programming attack is you can change the control flow by changing the return instruction, return target address, right? Return address. You can also change the control flow by changing the indirect branching. So indirect branch is jump register, right? Jump register means based on the register content, you can jump back to jump. You can go to any location. For this location, the register content is usually fetched from this table, that is jump table. If you change the jump table, you can change the flow. Okay, so that's what they're suggesting. Okay,
That's right.
okay, that's right.
And another background knowledge is control flow integrity. This is a solution. This is a powerful solution against the code reuse attack.
Okay,
But they have some quite big overhead.
what is
22%.
control flow integrity?
Sorry.
What is CFI?
CFI means program execution flow strictly follow the certain paths.
How can you enforce? So somehow they are enforcing original control flow, right? Because they are changing the control flow, right? How do they can enforce their original control flow?
Actually, that is not described
Okay.
in this paper.
Okay. And if they do that, they have this kind of performance loss.
Yes.
Okay, that's right.
So this is the main idea of branch regulation. This is the main idea is very simple. Simple control flow invariance is provided by simple hardware, and branch regulation works by imposing just 3 rules. Let me explain the 3 rules. The main idea. Yes. The first return statement means a return instruction should point the address to saved by call instruction. It means they also use some stack. It's called secure call stack, and they save the return address and restore it and compare and they equal. BR check passed and it's not equal. The BR check failed.
Tujin.
Yes.
So you said they are suggesting some new structure, step.
Yes.
Do you need to use this kind of step? My question.
also means also implement some stack.
That's right. Additional structure.
Yes.
I don't think we don't need that. We can implement this function easily with existing hardware
Without stack?
without extra step. Can you do that?
How can I do that?
Do you remember return address step?
Yes.
It already has all this information.
But they also means secure code stack is software, not
But you
hardware.
don't have to use this extra software. You can use the hardware already, right? So if the return address is different from the top of RAS,
Yes.
then you should ignore this because you can trust your hardware, but you cannot trust this kind of return address because it can be manipulated by virus. Understood?
Okay.
So they don't have to use software step. So using RAS or RSB, you can implement this function easily. Right? But the second idea, indirect jump, what they do?
Last two rules. In order to check the last two rules, we should know we need to determine where a function begin and end, because actually I don't know exactly, but by preserving these two rules, we can prevent
So you don't.
abnormal.
You didn't study in detail.
Yes.
Let me have your point. So he's checking the boundary. If their indirect jump goes to outside the function boundary, then he thinks it's somewhat illegal. Okay? And I think indirect jump can go to anywhere. And he's assuming indirect jump can go to some within the function.
Yes.
That's his
Same
assumption.
function.
Right, but it doesn't have to be. So I'm not sure whether this is valid statement or because in general programming allows your indirect jump can go to anywhere. Okay, but this can be easily checked. Okay, so each suggestion is just simple one statement. It's like using the hardware it can be implemented easily. Okay, what's the third one? Core or function core. What they are doing. Check if function entry. Okay, so they also careful for updating or writing return address because return address should be safe, right? Because it should be protected from illegal update.
Yes.
And what they are doing, whether any path is illegal or legal path to this return address update. Something like that, right?
Yes.
You understand? And this can be easily done. And actually, what I have done this and more complexity for my previous paper, which we have some patent and I have award also for buffer overflow attack. I can prevent all this and also more severe attack.
How about performance?
Performance, a little bit of, I don't know, maybe 2% or that amount of degradation, but they can prevent all kinds of buffer overflow attack. Buffer overflow attack can occur to the stack or to the heap also. This may lead to the stack, right?
Yes.
Okay, so this is subset of my idea. I guess. Anyhow, these are the actual ideas.
Yes.
You can do this simply, you can implement similar things and it can be easily also evaluated. You can work on this idea because I have worked on this idea before. And this is simple. I can use my question. So how much performance branching, I don't have to look at the detail, I guess. I understand. How much penalty in terms of performance? This much. Compared to control flow integrity, their scheme has less overhead, but that's what they are saying. From about 0 to 1% to maybe up to 2%. Coach, this has almost nothing. It should be very, very simple because my previous proposal is I can even they modify, I can go backtrack and recover the original state. But they don't have this backtracking. They just
Yes.
prevent, right?
Yes.
So in terms of compared to deadlock, there is a deadlock prevention, avoidance, and recovery. Okay? In terms of overflow attack, they just propose prevention. My proposal is prevention, and there is prevention proposal, 0% overhead. And also, you can recover about 2% overhead. So it's actually better than this one. But they are targeting, instead of buffer overflow, which many people address, they are targeting the another issue, which is reuse, code reuse, which is a small portion of buffer overflow. Okay?
Small portion.
Yeah, because usually virus codes are coming in and they are learning virus code instead of using library. Right? So this is one kind of buffer overflow, but this doesn't cover everything because they come with their own virus code they cannot protect. This is only for reuse. And similar mechanism can be applied to the general buffer overflow. I don't think nothing new.
Yes,
in my opinion.
you're right. But the one unique idea is they implement some. Let me show you some architectural support this idea.
What?
Yes,
Which one?
they implemented some kind of cache. It's called function-bound stack.
Okay, that's not that.
The only purpose is
That's not that interesting. I can assume
Okay.
what they are trying to do. Simple. Okay? Maybe you can read my paper also
Yes.
and compare and think about some solution for this kind of code reuse or some other issues, because buffer overflow is the most important issue in security, computer security.
Yes.
And most proposal come from the network or software. Software is usually patch or recompilation or recode, okay? And you can do operating system support. Operating system, usually this virus code, they are trying to fetch instruction from the stack. And you can disallow. You only allow instruction fetch from the text instead of stack, then you can disallow this kind of buffer overflow. But this is someone using the system library, so they are targeting some different problem, but their proposal is traditional. Okay? And think about this kind of issue if you're interested. And maybe not just for PC and servers, it's not much interesting because many people have looked at this problem before.
Yeah.
But for smartphones and mobile device, there might be different flavor. It might be more interesting, and there might be more issues, and there might be some different flavor of proposals can be done. Okay? So think about buffer overflow or code reuse in smartphone and mobile device. And you can read also my paper and think about solutions and using these solutions.
I do that.
Okay. Let's go to the next one.
That's all.
Minji.
Okay, the paper title is Intercore Cooperative TLB Prefecture for Check Processor. This is Miras Plus 2010. So the TLB management, there is two types of TLB management, and one is hardware managed TLB and the other is software managed TLB. Hardware managed TLB has no need for expensive interrupt, and pipeline remains largely unaffected, but there is drawbacks. OS cannot employ alternate design. So software managed TLB has flexibility since the OS controls the page table work, and but misanderlize also instructions, and it may itself in the instruction cache. And data cache may be protected by the page table work. The author suggests messages, they analyze some TLB myths on multiprocessors. CMP means chip multiprocessor, and CMP maintains per-core instruction and data TLBs. They have each TLB in each core. And the author's other paper, they figured it out from significant similarities exist in TLB myth patterns among multiple cores. The chart says there is similarity in these patterns.
Okay, so what is this? This TLB misread or what?
Yes.
What is,
TLB misread.
what is it? Inside parentheses, I cannot read.
One million instruction window.
1 million instruction?
Yes.
This is DTLB 1 million instruction. What? Can you explain the number?
Among 1 million instruction, there
Oh,
is
I see. How many messages? And this is two applications. Two different applications. And this is for each core. And there are some fluctuation a little bit. Right?
yes.
And what do they run? What did they run from this implementation? It's quite similar or it's quite about the same, but they are arguing? Or what?
Similar pattern. There is similar number of
Message.
yes.
So regardless of cores, the number of messages are about the same. That's what they are saying. And this number of messages are about the same for each application,
Yes.
for each core. Okay. Not that new, okay.
So they categorize this pattern as two. So one is ICS intercore shared TLB misses, and the other is intercore predictable stride TLB misses. The intercore shared TLB misses means among cores they access same page entry.
So one core, there is a TLB miss.
Yes.
The same entry is missed by another core.
Yes.
Okay, the second one, what is it?
Second one is stride pattern is similar in core.
So here, what is the stripe? What's your page number stripe?
Yes.
Okay, so it's not the same page, but the TLB message occurring to different page, but there is a stride between the page number.
Yes.
That's what they are saying.
They-
And they can do prefetching for the second one. And the first one is if you process the first one, then the second one will be covered automatically. This one, because they are it's to the same entry. If one core is handling the myth, the other core myth will be handled automatically. Right? And this is can be done by previous skip, any skip. Right? And this one, you can do prefetching for page number stride.
Yes. The opera use
Both of them prefetching.
yes.
And the prefetching means before you miss, you prefetch this, you analyze, you prefetch TLB entry earlier.
Yes.
Okay.
There is they use two schemes. The first one is later follower prefetching. They reduce ICS misses. If a core TLB misses on a particular virtual page entry, other cores will also typically TLB misses on the same virtual page entry. There is bad prefetch. There may be bad prefetch. The bad prefetch may be harmful in that it will be unused, and the prefetch may be harmful in that it will affect existing PB entries for
Okay, so this is more like a stream buffer, right? Do you remember stream buffer? So you add this kind of stream buffer called prefetch buffer into every first core, and you check this pattern if they are accessing the same entry. Do they find this pattern? Whenever they find the pattern, then they match the same pattern, then you put this page table entry in the follower, this prefetch buffer. which is actually string buffers. Okay? And what's the other idea? And it's actually explanation of that.
Yes.
Okay, not different. Nothing new. Okay. Okay. And to use to be saturated counter, why?
The other thing thought it's over-aggressive scheme because every time TAB misses occur, they prefetch to another core, so they
can control this prefetching.
yes, by confidence estimation.
Okay, so if the saturating count bimodal predictor is saying it was predicted correctly last time that you predict
Yes.
you use. If it's zero, then you don't use.
Yes.
Okay, simple. You can do the similar things, right?
Yes.
It's not that easy, difficult. Okay, so this is all that explanation, nothing new. Okay, this just based for prefetching.
This scheme is used to reduce ICPS misses, to record repetitive distance pairs to find the next predicted distance and hence the next virtual pages. So the goal is finding the strike patterns.
Okay, how do they find strike?
They use distance table. So it is shared among cores, and they have some information like the 1, 2 or 2, 1, like this.
This is page number?
1 is previous strike and 2 is like next strike.
Okay.
They store predicted future distances in distance table.
Can you give some example? It seems quite simple. Can you give an example? How do they strike? Strike means for array reference, if you access A0, A4, A8 and so on, then if you use 32-bit word, then you actually increment your address by 4 by 4, 16, right? 16 can be a strike, right? You automatically increase your slide and you can prefetch to strike addresses. Here they use page number 0, 4, A, 12, and this stride is 4, right? Then how do they, what kind of information do they have to maintain to do that?
Core 0, page, access page like 3, 4, 6, core 1, access pages 10. They
Stride is 4.
store the stride.
Okay, they store the stride of local stride,
Yes.
not intercore stride. But intercore stride in this case is 4, right?
Yes.
Intra-core stride is 1 to whatever. But how do they can figure out the intercore stride in this example? They cannot.
They can.
Why?
They didn't use intercore stride.
They don't use intercore stride. How can they help this one? So there is no stride. This is some kind of arbitrary number. Stride means constant gap between each reference pattern. That is the stride. There is no constant gap because 1, 2, and random number.
The author says when multi-threading, the different cores may access same stride pattern pages.
Also, they use 1, 2, this kind of
Yes.
sequence or what is it? Sequence. They use actually sequence, not stride.
Yes.
The stride, I was guessing that stride in this case I was 4 because intercore, but they are using sequence instead of stride.
Yes.
Can you use both?
Maybe.
And which one will be more useful? You don't know, right?
Yes.
I don't know either. So it's actually they are using the sequence. The reference patterns are about the same, the gap between this page number. Because if you do parallel processing, you have large amount of, you do loop level parallelism, then you actually cut your array into the same section, and there can be a stride, right? Either stride or sequence. And you can use either or both, and they are using actual sequence pattern. Okay, and that's what they are calling stride.
Yes.
And they don't evaluate this kind of interval stride in this paper. Okay, so that's the one-to-end. Distance pairs means, so you can use the sequence 1 to whatever, right?
Yes.
Or you can use just page number. I don't know the difference. But why do they use this pairs instead of just page number? From the page number, you can extract this sequence, right? Why do they use pair? This is redundant too. You don't know. You didn't study enough, I guess. Okay, next slide.
So the result is
Okay, on average, how much they can improve using their prefetching?
on average 46%.
46% in what? Not the execution time, it's just for TLB message.
Yes.
So they can reduce TLB message this much on average. In terms of execution time, how much they can improve? They didn't give. So execution time ratio might be very small because TLB miss accounts for only small portion of total execution time. Okay? Is that all?
Yes, sir.
Okay. Okay, so how many students do you have? One? More? Okay, the final talk. Okay.
Hello everyone, I am Ho Young-tam from Goryeo Signal Processing Lab, and now I will start my presentation on rethinking DRAM design and organization for energy-constrained multi-cores. The author of the paper are introduced in this slide.
And which conference or journal?
ISCA 2010.
2010, so it's about 3 years old. Okay.
These are the contents of my presentation. Abstract is referred firstly, and background of the paper is introduced, and motivation of proposed architecture.
You can go directly to the overfetch.
Overfetch.
This is quite simple. Issue. What is overfetch? Explain.
The end of background covers about the overfetch problem. If the requested data is present in the row buffer, then the memory controller is aware of this, and the data can be returned much faster because the requested data is in already a row buffer. But if the requested data is not in the buffer, then the current open row has to be closed and closed it before opening the new row. So this policy is about the first one of two alternative options, which is an open page policy, and the other alternative option is a closed page policy. It is to prevent the closing of the row from being on the critical path for the next row buffer miss.
It's not overfetch. Do you know what is overfetch problem? So what problem is this paper is trying to address? What is the problem statement? Let's start from the beginning. It's not overfetch.
Because the requested data is a portion of the raw buffer data.
Mm-hmm.
So the thing is optimize the architecture and operation to only read the requested data, not to read all the raw buffer data.
So it's actually overfetch. Okay,
Yes.
so you are fetching, so every read includes fetching a row, right? And you don't have to fetch the entire row, you only need to fetch column. So you are fetching too much data,
Yeah.
right?
Yeah.
Okay, so what's their solution? What they are doing?
So they propose 3 architectures. The first one is selective inline activation. In the conventional DRAM architecture, the raw address comes in first through shared address pin. So in conventional DRAM, it activates all the raw.
So
And
you
then-
actually have this mask bit, and you are masking off unrelated section of the row, and you're unmasking only the selective
Yes.
columns.
Yes.
That's what they are suggesting.
So
Okay, what other solution? That's obvious. Okay, what other solution? There's some additional overhead. Okay, and
So-
what others?
we have to add some
Extra
extra AND gate here.
wires and AND gates. Okay.
By using this, we can reduce dynamic energy.
Okay, I can agree. What's the other second solution?
Second solution is single sub-array access. A single access activates multiple chips and multiple large arrays within each chip. So the thing is to make a sub-array of architecture much smaller. Smaller to cover the requested cache line. To make an extreme example, make the subarray as wide as just one cache line. Then you can reduce the overfetch problem.
You don't have to make the subarray as big as the cache line because this is inside DRAM.
Yes.
Because usually DIMM card has many DRAM chips, so they only provide maybe if you have 16 chips as in the normal DIMM card, then each DRAM chip needs to provide 4 bits, right? So you don't have to 4-bit lines are enough. Right? They are considering consecutive access, such as
Like interleaving.
uh-huh.
Interleaving.
Excuse me.
Like 4 DRAM, 4-bit cache data.
Okay, so let's say you have 16 DRAM, 8 DRAM chips on front, on the back you have 8 DRAM chips. Usually system buses are 64 bit. Okay, then each DRAM chip needs to supply only 4 bits. With 4 bit, they are all operating in parallel.
Yeah.
Okay, 4 by 16, 64. Okay, but that's 8 bytes, right? Cache blocks are maybe, let's assume that's 256 bytes. 256 bytes means you need 32 transactions consecutive, right? So 4 bits for each cycle, but 32 transactions, 32 cycles. So they have counters, right? So 32 times 4, so maybe 128. So that's what they are saying, cache line. That's the maximum. It's not should not match with the cache line directly because you have to consider many chips are working in parallel.
Yeah.
Okay, and what they're suggesting is actually nowadays DRAM chip there is not a single 2-dimensional array. You decompose it into multi-bank. Okay, so in here there are 8 banks, and if you access only one bank, you can reduce the power by 1/8 because you are operating only one bank instead of entire bank. That's what they are suggesting. No? and it's already done in the actual DRAM because they are all consist of multiple banks inside. But what they're suggesting is the single sub-array is same as bank, right?
Yeah, that's just an extreme example. Make the subarray as wide as cache line.
As wide as cache line, I don't know whether explain. It should not be less wide because many chips are working in parallel. Okay, you can consider the cache line size, right? And you can reduce the width of this data path because many chips can work in parallel. And this subarray seems like bank, and my question is bank is already employed in the DRAM chip inside. They operate only one DRAM bank at a time, but they can work in parallel, pipeline fashion because the one DRAM chip is accessed, it takes time because row access or column access takes quite a amount of time. But cycle time is different. In next cycle, new request comes in, it can go to different bank, right? It can work in this pipeline fashion. It's somehow in 8 cycles later, right? 8 banks are working in parallel, servicing different requests. That's already done in the DRAM. That's what I'm saying. So this might be an old proposal. Okay? Okay, what's the third idea?
So by using this architecture, we can remaining inactive subarrays can be placed in low power
That's right.
slim mode, saving the background energy.
That's obvious.
The third idea is about ECC for the second proposal, which has conventionally one DRAM chip is added for 8 DRAM chip to use ECC and to store the parity bit.
1, 2, 3, 4, 5, 6, 7, 8, 9. So you add one parity, 6, 9 ECC.
Yes.
Okay. So
But when we are just accessing small segment of the data, we have to read all the 9 DRAM devices to use the parity bit.
you can put this parity inside each
Yes.
DRAM instead of across DRAM.
The
Then
simple
you can-
ECC can be added with smaller
Within
segment.
DRAM.
Yes.
That's what they're suggesting.
Yes.
Okay, that's kind of obvious also.
So the main assumption is that in the previous days the area is the most important thing, but nowadays the power consumption is important. So I think so it is a little bit obvious, but they say it is.
This is not done in
Important.
practice, so
Yes.
they are suggesting.
Yes.
Okay.
So when we are using the C checksum bit here, we can can detect error, and then using the parity bits, we can correct the error by reading all the DRAM devices. So it's a conclusion of the paper. The memory energy reduction are substantial for both dynamic and background components. Fetching the exactly cache line with the second proposal, SSA, can incur performance improvement or degradation according to the different applications.
Okay. So it's about a little bit of configuration can reduce the energy and power, and performance sacrifice is almost negligible.
Yeah.
But their proposal is somewhat quite obvious, and it's quite already implemented. So this area is moving fast because its demand is quite high. There are more new proposals after this paper. So there are more new ones. So this is quite old, a little bit outdated, I think. Okay? Anyhow, thank you for your talk.
So, and the third with the
Okay, you don't have to give that much detail. So we understand. Okay?
yes.
So actually, for each talk, I need to give you some time for questions from students, but but before I go to clear, I want to finish this class, and next week we have a class, so I controlled your presentation. Sorry about that. Okay? But anyhow, you did a good job. I understand your talk. Okay? Okay. And no more presentation. Okay? So we complete our presentation. Okay? So. Okay, thanks for your talk, and this is final day, so see you next, maybe I might not be here, but prepare for your final exam, okay? And I think most of your students participate in class very well, so, but you should prepare a lot, because the questions are kind of not easy if you don't prepare, okay? And if you prepare to give reasonable answers, I'll give you reasonable grade, right? But too much low, maybe you will get C or maybe D. If it's reasonable, then I'll try to give you final grade. Okay? Okay.